Welcome to Almost Here, Round the Corner Future Technology podcast with Richard Jacobs. Future technologies poised to transform our lives for better or worse are the focus of this podcast. Almost here means these technologies are now here and starting to be used, or just around the corner, from Bitcoin to artificial intelligence, 3D printing, blockchain, virtual reality, and more.
Hello, this is Richard Jacobs with the Future Tech Podcast. My guest is Thom. He's the Director of Software and Cloud Services at DWave. And DWave does quantum computing services, which we'll get into. So, Murray, thanks for coming.
Thanks, Rich. Yeah, great talking to you.
Yeah, so tell me about DWave. What's the premise of the company?
So DWave Systems is a quantum computing company. Our mission is to unlock the power of quantum computers for the real world today. We've been doing that since just approaching 20 years now, building practical quantum computers and making them available to our customers and users and developers.
Yeah, I've talked to several people about quantum computing, the technical side, but I wanted to start differently with you. So are we actually close to having quantum computers in use by industry, and what will be some of the first uses when it does come, in your opinion?
Yeah, absolutely. So we are in fact already seeing users in industry making use of quantum computers. So DWave has been working with customers and collaborators for 8 years now on our quantum computing systems. We were actually one of the earliest providers of cloud access to our quantum computers. And in that time, our customers have developed more than 100 early applications for our quantum computing systems in areas from optimization to a variety of projects in machine learning, as well as, and probably most notably and most recently in material simulation work. So for an example, Volkswagen has been working with us for some time now on really sort of fundamentally approaching the challenge of let's not work on sort of synthetic benchmark applications with data that we're sort of making ourselves. Let's work with industrial data, and they've really been targeted on looking at traffic flow optimization as sort of a proof of concept project in terms of demonstrating, where in that problem they're going to be adapting quantum computing, mapping their problem to that space, and running it on industrial data that they have. Public data on the positions of taxis in Beijing. And now, having completed that project, they're looking to extend that to a real-world application workflow, which will include, actually enabling users a year from now to be able to sort of request routing information through their phones and have that basically go through a hybrid system where it actually does some optimization through classical resources and also makes calls to quantum computers to basically suggest to them sort of real-time routing in terms of their route through traffic.
So you're saying, okay, so this is when someone wants to hail a taxi in Beijing. Right now, obviously, we use classical applications to determine which taxi is closest to that person and which one should be assigned to that person, right? And you want to use quantum computing along with classical computing to make that algorithm, faster? What would change by using quantum computing with it? And at what point would you use quantum computing versus classical, and why is it better? For that example.
Yeah, that's a good question. So there's let's say if we were to take like traffic flow optimization and try to break that down into two subtasks. There are some tasks where you basically say, I have 2 points on a map, and I know that this particular car wants to get from A to B. What's the shortest path algorithm? And there's efficient classical algorithms for basically looking at particular routes and basically saying, okay, this is the shortest path that's available to them. But if you have a large system of cars, you don't necessarily want, and this is sort of Volkswagen's vision, you don't necessarily want like 5,000 people to try to take that same route because the road doesn't have that kind of capacity. So once you've established, let's say, a variety of routes that cars could take, then you have an optimization that you need to do where the choices of the routes that the cars are going to take are related to one another. They have correlations. And as they begin to make their choices, other cars should sort of make choices differently. And that optimization is a more challenging optimization for classical computers to do. So that was the portion that they mapped to the quantum computer. And the quantum computers that DWave is building have sort of like a core function that they're running at the low machine level, and that is the effectively the difference that quantum computing can make for their applications is helping to make some of those more complex optimizations possible to do. And in some cases, alternatives include making classical alternatives to them, and maybe those are working well, but they don't particularly scale well. Maybe they have to make approximations to solve them with classical computers that don't yield the same results as if you were able to solve the problems directly. So depending on which application you're looking at and where our customers are using the technology, there's sort of different benefits that people see realized. But the ultimate goal is to get solutions to those types of problems, faster or with better quality, or even matching quality and time, being able to do it less expensively.
Well, it seems like traditional computers work best when there's an algorithm to solve something, and then they can just, churn through it. But quantum computing works more of like in a brute force fashion, or like when there's a heuristic, there's no specific algorithm to do something, but it can run so much faster and in parallel that they can still get good results when classical computers wouldn't at that point.
Yeah, there's this interesting thing about quantum computing. So often when we talk about quantum computers, we talk about what is it that's making them different. We have the computers on our desktops and our laptops and on our phones. They're inside there are chips which are basically processing information for us, and at DWave we're making similar chips housed in different systems to get them at the right operating conditions. And the fundamental building block there is a bit of information, which is then made quantum mechanical, and so the quantum bit is referred to as a qubit. What's interesting about that is that a qubit, it's a binary system. When you measure it or evaluate it, it can only be a 0 or a 1. But because it's quantum mechanical, when you're processing with it, it can be in both states simultaneously. And what's significant about that is that if you create a memory register out of those quantum bits and you want to store information in that memory register, it can now contain all of the possible states that the memory register could house. So if you have, let's say, 2 qubits, it could basically be in all 4 states at the same time. If you had 10 qubits, it could be all 1,024 states at the same time. But if you had 300 of these quantum bits, the memory register could be in more states than the number of particles in the universe. So what's really interesting about that is that as we're making our quantum computers, and as people are designing algorithms for quantum computers, they're looking at that enormous sort of exponentially sized solution space capacity and trying to create algorithms which search that solution space quickly and provide you with high quality solutions. And that's what the processors at DWave do. So when you're programming a quantum computer, you may, in some sort of models of quantum computation, actually tell it how to use quantum mechanics in order to solve problems. But at DWave, we're trying to make quantum computers that are practical, that people can sort of use in application right away. And our experience is that there's not a lot of quantum physicists in the world, and there's not necessarily a huge number of people who want to learn quantum physics before they start programming the quantum computers. So the notion is that you don't necessarily have to control the quantum mechanics. You can actually set it up so the quantum mechanics basically works to find a solution for you. And the way I would characterize that, sort of using like a common metaphor, would be like programming a quantum computer is a little bit like making a maze, for a mouse, where you have some particular, space that like a solution space that you can kind of move through, and you have a particular goal, you want to get to the exit. But you know that your problem has penalties and incentives, it has barriers, and so you're basically, as a programmer, you're setting those up in the maze. Now, in some models of quantum computing, you are basically placing a quantum mouse in the maze, and then you have to put it into superposition and then move it through the maze and then get it to interfere with itself in order to make its way to the exit. But in the types of quantum computers that DWave is providing, you basically put a piece of cheese by the exit of the maze. It's sort of an incentive. And what happens is the quantum mouse then uses quantum mechanics to move through the maze to find that piece of cheese and tell you where the exit is. So, in some of the application building, what you're looking to do is you're looking to solve your problem. You want the solution to your application. Maybe the the traffic routing solution for your cities. And so you just want that mouse to basically move there as quickly as you can. In some cases, what you're trying to do is learn about the quantum mouse. You want to figure out how does it behave and what kind of problems is it suitable for. So you're constructing mazes and then seeing how it moves through that. And developers of our quantum computing systems are doing a little bit of both whenever they're programming our quantum computing systems.
So like in the mouse and the maze example, traditional computing, the mouse would have to go one way, and then, let's say it moves forward one space. Now it has to reevaluate and see, okay, can I go left, right, forward, or back? And it keeps moving. But it would have to go down X number of paths and then retrace. But with quantum computing, it sounds like you could simultaneously, I guess, quote unquote, try every path through the maze because of superposition and theoretically see the space and possibility all in 1 second, right? Or all in one processing unit or cycle.
Exactly. Yeah, Rich, that's absolutely on point. You're if you think about like an algorithm, it's like, okay, can you go left? Can you go down? Can you go right? Can you go up? Okay, and then take whatever move is sort of available to you until you get trapped, and then you kind of have to backtrack through. That's exactly like you're saying, the classical technique. And this quantum superposition is allowing you to sort of like move through the maze, penetrate through barriers using quantum tunneling, that kind of thing. And the significant thing about it is that, if all you had to do was like find like the lowest grain of sand in the Sahara Desert, that would be a relatively easy problem because of the number of grains of sand in the Sahara Desert. But in this case, you're looking at like vastly larger number of solutions than the number of particles in the universe. So just being able to step through the maze and sequence quickly isn't enough.
Well, what's interesting is that tells me for various problems, even if they've been solved, we probably don't know what the whole solution space looks like. And certain systems are so complicated that with quantum computing, you might be able to see, different solutions within the same space that we never suspected were there, or we couldn't see because we couldn't see the whole space at once. I know that's like a vague way of talking, but I think you'll understand, right?
Yeah, absolutely. It's think about it a little bit like a mountainous landscape. If you're very quick at running downhill, you might be able to run down one slope and get to the bottom, like get to one of the low points in one of the valleys. But what do all the other valleys look like, right? Are there other lower valleys? What is that? Maybe every other point in the landscape is higher, but you're not quite sure. So in fact, that's actually very related to some of the quantum material simulation work that's happened this last summer. We published papers in Science and Nature showing how you could simulate and evaluate these exotic properties of materials using the quantum computing system. It's not enough to just know one way that the material could end up being configured. You sort of say, here's all the particles that are in my material, and here's how they interact with one another. Now, is this material going to be magnetic, or is it going to be non-magnetic? You're looking to find out if the material, what kind of properties it's going to take in terms of whether it's going to order or whether it's going to be disordered. And really, in order to find those solutions, you need to know something about the density of the solutions at particular energy. So you need to know about several of the valleys, or like a statistically significant number of the valleys. And exactly like you said, previously that might have been a mystery to us, right? Because there was just more than we could possibly count. But quantum computing can help us to evaluate what some of the structure of that solution space looks like, and that can be really important for some of the calculations that people do in machine learning and artificial intelligence. I mean, it's heady mathematical statistical stuff, but that is related to some of this computational complexity that researchers and developers and data scientists are trying to program their way through in this space. Is basically looking at like what are the shapes of some of these solution spaces, because that affects how the machines that they're training, it affects how they learn.
Yeah, I could see. So do you have is there so the number of particles in the universe is what, like 10 to the 80th, 10 to the 80 approximately? So do you have a chart, in your office or in your mind of other problems? And if we start with like the number of particles in the universe, 10 to the 80th, what other problems have you looked at, and what is their order of magnitude? Because now we have like an anchor,
Well, the interesting thing is, when at DWave, when we made our 500 qubit quantum computer, it was searching through solution spaces that were already larger than that 10 to the 80th. And now we're at the DWave 2000Q, which is 4 times larger. The numbers are getting, it's one of these things where the numbers are so big, it's almost like it's hard to kind of fathom them anymore. And the interesting thing is, as we're working with our customers, so for instance, as people are trying to take real world problems and then map them into these expressions of like what they're trying to get done, they're even larger still. So in many cases, what we're trying to do is we're trying to help them, contain, or let's say extract some of that complexity so that they can basically use the classical computers for what they're really good at, some of the data analysis steps, or some where there are fast strategic algorithms to move through things, but then also extract these really complex optimization problems so that they can basically map those to a quantum computer. So like Recruit Communications in Japan is looking at web advertising. They have a huge amount of expertise in providing, advertisements for people in terms of like hotel recommendations if they're, looking for a particular hotel in Tokyo. And they have systems where, an individual user is clicking for a site and they have an opportunity to place an ad. That computation takes place really quickly, and they have high quality algorithms for that. But what they found was that they wanted to do further optimization where they were like pacing the budget of how they spent money on advertisements throughout the day. They didn't want all their advertisements to go out before 9 a.m. And so there was an overarching optimization task that they wanted to do every time they wanted to evaluate if they wanted to go with their algorithm's recommendation and place the ad or not. They would also review, how does this fit within the optimization for our daily budget? And they put that step on the quantum computer and ran that. So, that's an optimization problem that we kind of see every day, or that's sort of like a very real world example. And it's interesting to think about the fact that the mathematics that underpins that can be as complex as that. And in those kinds of solutions, customers like Recruit Communications are looking for just very fast, high quality answers.
So what are some of the solutions that you've been working on or you've seen that were most fascinating to you? I don't know, you don't have to name the companies, let's say, or if you can, great, but what kind of things have you worked on that were like amazing to you?
Well, I mean, the nice thing, let's see here. So the nice thing about working at DWave is that we have some quantum computing hardware that's working at a large enough scale that people can really use it for building and running sort of practical application development. And once you can kind of get to that point with 2000 qubit, it's I mentioned the quantum material simulation, which is fascinating. It's related to a subject, some theory that won the Nobel Prize in 2016. And what's fascinating about that was that as we were looking to write up the results, we had let me actually pull this up. We consulted with the professor who had actually been one of the winners of the Nobel Prize in 2016 related to that subject. And at that time, the Nobel committee or organization had sort of put out a press release saying, hey, the hunt is on now for exotic materials of matter. And that scientist, Dr. Michael Kosterlitz, said that that work represented a breakthrough in the simulation of physical systems, which are otherwise essentially impossible. So, that's what's fascinating for me is this notion that like we could take some problems that previously you needed a supercomputer to solve, or maybe there were some problems that we just couldn't solve at all, and now we can do them with quantum computing. And as quantum computers grow, that's going to be the only way you would solve the problem. And so, when I'm looking at all of the other applications, what's really fascinating for me is like how real world they are. The traffic flow optimization, the providing hotel recommendations for travelers. Denso, we're working with in Japan. They're really interested in like optimizing their factories. So they have robots that move through factories, and they want to optimize their movement so they have minimal downtime. And in October we launched Leap. It's a quantum application environment where developers it's sort of the only cloud environment where developers can get immediate access to a quantum computing system, learning resources, and community forums. And one of the applications that I heard discussed from a developer was optimizing the ice time choices for his sun's ring-it league. And I just kind of think that's so cool that quantum computing can be accessible to the point where we can do, work and helping solve problems for people in their everyday lives. And, when we're talking with, our customers and partners, or when I'm talking to new, folks who are new to quantum computing, what they're searching for is, what is this new technology? What kind of problems can it solve? And what's exciting in their mind is like, what if that happens, that thing that happened in material simulation happens in this application space where previously, I had a technique for solving this problem, but 2 years from now, the only way to solve it is going to be with a quantum computer. Because many of them are sort of saying, well, how is my workforce going to adapt to that? How is the economy and the developers who are programming for these systems going to adapt for that? And that's part of the reason why we have this quantum application environment out, is because every one of us who comes to quantum computing is both a teacher and a learner. Where we need to be able to interact with that community through those forums or through those conversations so that we can learn from the community and their common experiences, but we also have our own knowledge to bring, expertise about the application space that we're working on, or maybe, mathematicians are bringing their math or statistics skills. And it's exciting to see that system, that community come together. It's going to be the foundation of a new economy in the future. To look at those kinds of practical applications. So that I don't know. It's not a very, very specific answer, but it's exciting.
Well, what are some dream applications that have been out there either for, just recently or maybe for a long time? Maybe stuff that's been around for centuries. I don't know. What do you see quantum computing being able to uniquely tackle that, again, has been the hope or the dream of many people?
Yeah, I think that I would say that probably the thing that really gets me going, that really keeps me focused on it's helping to make some of the complexities of quantum computing simpler for people are ones that really touch our lives. So a few years ago, I had an opportunity to visit with a researcher at the Children's Hospital of Los Angeles who was studying research and medical treatments for childhood leukemia. And they sort of say, we have a treatment for childhood leukemia. It's not everything we'd want it to be, but it's generally quite successful. And their goal was, what they would like to do is be able to predict whether or not a particular patient is going to, their bodies are going to be receptive to the treatment. Because if they could predict that they weren't, the treatment is quite tough. And they wanted to save them from that. And if they could help to segment the group of patients into those for whom the treatment would work and those who wouldn't, then they could get closer to personalized medicine. They could start pouring research dollars into finding the treatments that would work for the group who weren't responding to the treatment that they did have. And, the researchers were so motivated by this mission of what they were trying to do. And they had all of this data. They had metabolic data, they had genetic data, they had gene expression data, all sorts of data. And they just needed tools to help them better detect patterns in this data set. And these techniques that the quantum computer can contribute, they're really valuable from the sort of machine learning, artificial intelligence, pattern recognition perspective. They allow you to create a model of the world that's going to try to match some pattern that you're seeing in data. And so, I would really love to see that come together, to see the technology come together with the researchers who have the medical expertise and the machine learners who have the programming and algorithms expertise to come together to create a solution in that space. I think that would be tremendously exciting for me. Having worked at DWave for 16 years, I would really feel like all that time had really had a lot of value and meaning, seeing an application like that come to fruition.
You said you have a machine that has the power of what, 2,000 qubits? Is that the largest one you have, or?
Yeah, that's right. We have our latest product is the DWave 2000Q. It's got it's a processor chip designed with 2,048 qubits in it, but of course with fabrication processes, not every qubit works out. And we have customers with 2,000 Qs on site. Google and NASA, for instance, have a 2,000 qubit at their location. And we also have a number of customers who are accessing our systems remotely here in Vancouver and programming on the DWave 2000 Qs.
Is there a breakthrough point? I mean, I thought that in the world that didn't even exist, a 100-qubit computer. I'm surprised you guys have one that's so large. But is there going to be a breakthrough point? Like, what's the goals of DWave? Are you working on a 1,000-qubit one? Will that be just unbelievable, or do we even need to go there with that scale?
Well, we're working on our next generation devices, which the interesting thing about quantum computing is that we're often measured. We often sort of talk to each other about how many qubits are in the systems that we're building, but there's a lot of other features of the computers that we're also simultaneously trying to work on improving. So, for instance, the number of qubits basically determines sort of the capacity of your quantum computer to take a portion out of your problem. The bigger it is, the more of your problem you can fit into the quantum computer. There's also programming devices between the qubits in your quantum computer, which are couplers. And these are some of the programming parameters you use to kind of create those walls in your maze, those relationships that sort of tell you where there are penalties and incentives in the problem that you're working with. And so in our next generation device, we're also looking to increase the connectivity of our processor, because that's going to make it easier for our users to map problems to the system. And then we're also working on improving the quantum mechanics. So we're looking at making changes in the processor so that the quantum mechanics is longer lived. It's better protected from its environment, so that it's not disturbed as frequently. And that is basically going to, in that maze analogy, that's going to mean that the mouse is better able to use quantum mechanics to sort of work its way through the maze and find the solutions for you. So I think there's always going to be an ongoing quest to grow larger quantum computing systems, make it easier to map applications to them, and give our developers and users more control over them. Early on, we also thought similarly, like with the information capacity of a quantum computing system, all you have to do is get up to 50 variables and classical computers can no longer simulate them. But what we have found in practice is that, not surprisingly, every time you're building a real physical system, it has imperfections and noise to it. Also, the guide for how complex a problem a classical computer can solve is also theoretical. So maybe it's not possible to prove that a classical computer could solve a 50-variable problem in the worst possible case. But when you actually start creating the instances and solving them, many times classical computers have heuristics which are very efficient. So it becomes a difficult challenge just to find the problem, the one instance of the problem that they can't solve. So that's the nice thing about pushing up to the scale of 2,000 qubits. I mean, it was very challenging in the early days when we had our 128 qubit system that we sold to Lockheed Martin in 2010. And then when we were getting up to our 500 qubit system, we were really sort of pushing the boundaries. Researchers were coming into the space to sort of determine, how do we benchmark quantum computers and how difficult is it for them to compete with classical computers. But now at the 2,000 qubit scale, with that sort of research work I was talking about, we're really starting to see a lot of places, and we're hearing from our customers that they're starting to see the benefits of using quantum computers for tackling some of these complex problems. So it's kind of, you might think it might be a sharp line where once you cross, 50 qubits or 100 qubits or 200 qubits, nothing can be simulated anymore. But in fact, it's a little bit more like a spectrum, and you just start, it's like start working away from like the thin tail of very, very difficult problems, and then you start working your way up towards the thicker body of more complex problems that are routinely difficult to solve.
Well, if you were to picture like an infographic, of the number of qubits and the type of problems you could solve, and we extended it all the way out to like 1 million qubits, what kind of stuff would you see on the infographic? This is a game to play. What if I dropped 1 million qubit computer in your lap and say, here, what could you do with it? And what could you do on the way to that million? What are some thoughts you have?
Well, I mean, that's an interesting game to play, because when it comes to, so I'm trying to think, there's a couple of perspectives I'm coming at here. So if you build like the world's biggest quantum computer and it was perfectly implemented, and you were going to try to do with it what people have commonly thought of as being the application for quantum computing, like running Shor's algorithm to factor numbers, if you were to then test it by sort of randomly giving it numbers and saying, okay, factor this number and let's compare it to an algorithm, that would be it would actually be very difficult for it to compete in that test. It's sort of a funny case, but I mean, half the numbers that you would give it would be divisible by 2, right? And then, another third would be divisible by 3 kind of thing. So you have this sort of funny scenario where like that heuristic that you would run on a classical computer, which is try dividing by 2, try dividing by 3, try dividing by 5, try dividing by 7, it would actually be able to solve 90% of the numbers, factor 90% of the numbers in like constant time. So that's sort of funny. You do have to sort of think carefully. Even if you had a large scale system, you're really going to use it in a hybrid case where classical computers are going to do a large portion of the problem, and you're just going to reserve it for some really complex instances. But the other thing is that it's much more helpful if you kind of get the computers in stages, because you learn so much along the way. The complexity, even for the human developers, grows at each stage, and so they actually create tools and abstractions and utilities which then allow them to handle that complexity as the system grows in size. But if, just to sort of answer your question very specifically, I think that we're sort of saying, I mean, once you got up to a system of that size, 1 million qubits, there are going to be, even at the 5,000 qubit scale for the system that we're going to be solving, there are going to be problems that humans previously could never ever solve at 5,000 qubits, that now we're going to be able to create the solutions for. And it's not just going to go from like not solvable to solvable. There's going to be this massive time difference in terms of like how easily they can be made available. And anytime in humanity we've created an engine which can basically do something easily, which previously was difficult to do, like create a steam engine, for instance, which could actually like pump liquid out of mines or something like that. People were able to find ways to use it effectively. So I think that we're going to be able to discover novel materials which people can then use when they're designing all sorts of components, and we're going to be able to use it for we're at this age in our world right now where we're just bombarded with data, and sensors are very inexpensive, so we can just collect as much as we could possibly want, but we want to create insights out of that data. And some of them are, detecting cats on the internet are probably accessible to the kind of technologies that we have today. But even being able to fill out forms or to detect relationships between things, logical relationships, is something that still eludes machine learning and those kinds of algorithms. So I think those kinds of things are suddenly going to become unlocked. And then, I'm not sort of an expert in the science fiction space, but I think that that's really going to create possibilities I probably couldn't imagine today. So
gotcha.
That's cool.
Oh yeah, no, that's I just wanted to ask you to think about that for a minute. So okay. One last question. It's kind of a mundane one, but I don't know much about quantum computers, but I've heard they have to be run in very special environments, and they have to be run at like super low temperatures. So can you list a few of the factors that makes it necessary, or the conditions necessary to run a quantum computer, and why they're, I guess, delicate, if that's the word to use?
Yeah, absolutely. So so just to give you a little bit of a map of the space, quantum computers are this idea that, in the most general sense, of taking the weird laws and behavior, fundamental laws and behavior of the universe, and turning it into useful work. Right? Taking things like being in multiple states at the same time, being able to tunnel between states and make that do useful work for us. So that's sort of quantum computing, and there's many models for how you would do that. Between DWave and some of the other big players in the space, there's like 3 or 4 models of quantum computing that are being attempted in construction. And once then you've picked a model like as DWave has, then there's also many different ways that you could go about building it. And at DWave, we're building it with superconducting materials. So building it with like chips which have metals carrying, currents on chips that can flow electricity without any resistance. So I'm going to narrow my answer to that space. Then you have this chip doing this delicate quantum mechanical computation for you, and you can't even have like a photon of light hit it, because it'll actually change the state of the processor and maybe collapse the computation that you're working on, and then you'll need it to kind of recover. So we have really low temperatures, because that's where those metals can carry the current without producing resistance. So when I say low temperature, I mean like lower than 100 times below the temperature of interstellar space. We also have very low magnetic fields. So that's because we have loops of current, and loops of current can basically interact with magnetic fields around us. So those are also 50,000 times lower than Earth's magnetic field. And we basically also have this electromagnetic shield around it. It's in a room which is basically completely encased in metal, so that radio and cell phone signals can't come in and basically interact with the wires programming the quantum computer. And those are all so that as these qubits are effectively transitioning through their states, they can do this in a balanced way so that every qubit looks like every other qubit. And they can kind of, that quantum mechanical mouse can sort of move through the maze towards the exit, because if it gets interrupted on its way, each time it gets interrupted, it basically turns into a regular mouse. And then it basically hits all the walls in the maze, and it has to stop there, and it has to basically get back into a quantum mechanical state for it to start moving back through. So yeah, what you'd like to do is let the quantum mechanical mouse be quantum mechanical until it finds the cheese, and then measure it out at that point.
Okay, very good. So what's the best way for people that are interested to learn more? I have 10 to the 80 of more questions. How can they reach out and find out more and maybe suggest collaboration?
Yeah, we've tried to make as much of this available to folks as possible, because the barriers in quantum computing are really coming down now. So we have a lot of developers. We have 100 early applications developed on the system. There are thousands of developers programming quantum computers now and getting access to the tool. So if they go to our website, they'll see a link to our quantum application environment called LEAP. And they can go there, they can sign themselves up for free, and they'll see that they'll get 1 minute of access to a quantum computing system, enough time to run 400 to 4,000 experiments. You'll also see a variety of learning resources we've made available there, illustrated demos, in-browser programming examples and documentation, so they can interact with programs for the quantum computer, and also links to our open source tool suite, so they can go in, download them. They're Python-based and basically begin programming and building and running their own quantum applications. And when they have questions, if they're working on problems or they want help through the problems, or if they're coming from a particular industry and they want to see if the developer community has ideas on how to solve that problem, there's a group of community forums where they can post their questions, and there's a number of users there who are posting questions and asking and replying to them to create solutions. So it's very active. I think the largest growth is going to be in the application development space. It's really in the era of quantum application development. And it's also the time when the largest community of users can come in, get access, interact with quantum computers, and really learn and understand what they are and what they can do for us.
Well, very good. Murray, I appreciate you coming, and fascinating stuff. It's great what's going on.
Thanks, Rich. Great talking to you.
You have been listening to Almost Here, Around the Corner Future Technology podcast with Richard Jacobs. Subscribe to this podcast, post a review to discover more future technologies that are poised to transform our lives for better or worse, such as Bitcoin, artificial intelligence, 3D printing, blockchain, virtual reality, and more.